What is light? What's in an atom? These were deep, deep questions that scientists were trying to understand hundreds of years ago. And they didn't necessarily realize that they were actually working on the same concepts, that they were actually related. So part of the story of understanding the atomic structure and building theories on that, we have to also understand what scientists were doing in the physical world, trying to understand the fundamental nature of light. So the story really begins back in the beginning of the 1700s, when you had people like Sir Isaac Newton and others pondering the questions just about light. Is it a particle? Or is it a wave? How does it behave? Now, at the beginning of the 1800s, there was a remarkable experiment done by Thomas Young that I want to tell you about now. It's called the double slit experiment, and it goes kind of like this. So we all know that if you drop a pebble into a still pond of water, that you will get ripples coming out from that stone or pebble that you put in. So here we drop a pebble in and you start to get waves radiating out. These are disturbance waves. These are traveling waves through the medium of water. And we can describe that wave by its wavelength. So if we look at the disturbance wave in a side view, we can describe a wavelength, which is the distance between peaks of each wave. We use the Greek letter lambda for wavelength. And we can also describe the frequency, how many times a wave cycle will pass a point in time per second, or what we might call oscillations per second. That's the frequency. And if you measure the wavelength and you multiply that by the frequency, you can measure the velocity of that wave, of that traveling wave. So frequency, we use the Greek letter nu, and velocity, we'll use the regular letter v. Now, if you were to take a wall with a slit in it and put it by these ripples, these traveling waves in the water that we cause by dropping a pebble in it, you would find that when it hits this slit in the wall, you'll get a new disturbance coming out on the other side like this. And if I put a screen to measure the intensity of the waves that hit that screen and would plot a distribution of that, you would see that, of course, in the center of the screen, that's where most of the waves in the impact are, and then it kind of trails off on either side. Now, the double slit experiment starts the same way, except the wall has two slits in it, not just one. So now, as our traveling waves hit the wall, it passes through two slits, and through each slit, you get the same pattern that I showed you through the single slit. So from the top one, we would get a wave pattern that emerges from it that looks like this. And from the bottom slit, we would get the same pattern and it overlaps. Now, at each peak of the wave, if a peak from one set of waves hits the peak from another set of waves, like we would have here, and there's one here, and there's one here, here's another set of intersecting waves. Every time the waves intersect, they will amplify. And when the bottom of the waves hit each other, they're going to amplify as well, but in the opposite direction. So what you're going to get, and if I drew this properly, you'd see there's other intersections going off here as well. Now, what would you see on the screen? If we put a screen out here, you would see large peaks at the center that correspond to where the most intense waves amplified, and then as it spread out to left and right, you would still see amplification, but it would kind of be like this. The point being is that with wave behavior going through a double slit, this is what you would expect to see. A series of intense peaks on the screen that then get a little bit less intense as you move out to the right or to the left. Now that's a very different prediction than if we were to be shooting particles at this double slit. So what do you see if we were to shoot particles here? Well, particles, let's see. Obviously, if I shot particles at a single slit, right, so the particles spray out, they only go through the slit in one area, so they'll come out here, maybe there'll still be a little bit of spread, but they'll hit the screen and you'll still get a single peak with a, with a normal distribution around the side. What would you see in the double slit? Well, so in the double slit, you would predict you would only see 2 peaks on the screen because you're not radiating waves out from the other side of the slit. You're just shooting the particles through, and they get through the slit, and they might, bend around the corners a little bit, but you still would expect to see only 2 peaks and nothing else. So we've got 2 very clear predictions of what you would expect to see when waves pass through a double slit and particles pass through a double slit. So that's the setup. Now Thomas Young did this experiment with light, and what do you suppose he found? Does it behave like a wave, or does it behave like a particle? Okay, so here I have a slide and a laser pointer. And I'm going to show my laser pointer through this slide. And the slide, if you look really closely, has a series of double slits. You see that? And I'm going to shine the laser pointer through these various double slits. We've got the laser light, one point with my laser pointer, and now I'm going to put the slide in front of it that has the double slits in it. And look what happens. We have a distribution of multiple peaks on the screen, with the ones in the center being most intense, and the intensity then lowers as you go to left to right. And here I'm just showing you the slits. The distance between the double slits is changing, so I can make the peaks smaller or larger depending on the spacing of those double slits in the slide. So a very, very clear result from an experiment that has 2 very clear predictions. In this experiment, light is definitely behaving as a wave. And this concept that light behaved as a wave persisted for well over 100 years, while other experiments were being done to figure out other aspects of light. For example, James Maxwell's experiments defining what he called the electromagnetic spectrum, or EM spectrum. Now this was in the mid-1800s. And he demonstrated that there were really 2 oscillating fields, a magnetic field and an electric field. And they were basically oscillating in orthogonal orientations to each other. You can see that described up here. But these were still waves. They were like sine waves, the disturbance waves, just like I showed you in the previous slide, where you had a clear wavelength and a frequency. And once again, for wavelength, we use the Greek letter lambda. Right, this is wavelength. And we use the Greek letter nu for frequency. The units for wavelength, it's a distance from peak to peak. We'll measure that in nanometers. And the frequency, the number of times a wave cycle will pass a single point in time, is measured in oscillations per second, or what's now called as hertz, or Hz. And these again are cycles, oscillations or cycles per second. And as I mentioned, the wavelength times the frequency is equal to the velocity, v. Now that's when the wave is propagating through a medium, like a disturbance wave traveling through water. It will go at a certain velocity. Sound waves behave the same way, but that's a compression wave. Okay? So that's velocity in a medium. When there is no medium, so in a vacuum, there's nothing to stop these waves from moving, so they will reach a maximum speed, which we've called the speed of light. So in a vacuum, we have lambda nu is equal to c, where c is the speed of light. And the speed of light is approximately 3 times 10 to the 8th meters per second. Now, with this relationship, let's take a look at the entire electromagnetic spectrum. Whatever that electromagnetic radiation is, it has a measured wavelength and a measured frequency, but the product of those 2 will always equal the speed of light. So here's a figure from another textbook where we look at the whole range, and on one end of the range we have very energetic gamma rays, and at the other end we have very, very low energy radio waves. And the wavelength here in nanometers. So the very energetic gamma rays, they have a relatively short wavelength, 10 to the negative 3rd nanometers. So these have short wavelengths, And on the other end of the scale, radio waves, these have wavelengths of 10 to the 13th nanometers. Given that a nanometer is 10 to the negative 9th meters, that means that we have 10 to the 4th meters. That's the length. 10 to the 4th, that's 10,000 meters. That's the wavelength of radio waves. So these are very, very long wavelengths. The product of wavelength and frequency is always going to be the speed of light. So if you have a very, very short wavelength, that means you need to have a very, very high or fast frequency. And correspondingly, the long wavelength, so that's a very, very large number, 10,000 meters, so that's going to have a very, very low frequency. Now, if you can think about high and low frequencies, think about just some particle hitting a wall at a very, very low frequency. Here, I'll just use the sound of my fist on my hand here. It's hitting the wall at a rather, rather low frequency. The same ball hitting the wall at a very, very high frequency, you can see that there's a lot more energy going into that wall per unit time than there is if it's hitting it at a very, very low frequency. In other words, there's a strong correlation between the high frequency and high energy, low frequency and low energy. And as we all know, gamma rays, X-rays, these things will hurt you, right? These have very, very high energy. And radio waves, well, they're passing through you all the time. They don't hurt you at all. These have very, very low energy. Now, in the middle of this electromagnetic spectrum, you have this really, really small area here, the visible range. That's right, folks. Your eyes are electromagnetic detectors, and they can detect electromagnetic radiation that fall into this very, very small zone. And if we measure it by wavelength, it goes from about 400 nanometers to about 700 nanometers in wavelength. These are all the colors of the rainbow. It's the full spectrum. If you go just below the violet, well, that's ultraviolet or UV. And anybody who's stood out in the sun for too long without sunscreen knows what happens when you have too much UV radiation on your skin. You get a burn, you get a sunburn. High energy electromagnetic radiation that's hitting your skin. Whereas if you go to the other end of the spectrum, if you get a little bit longer than 700 nanometers in wavelength, you enter what we call the infrared region. Infrared, those are heat waves. They don't really hurt you too much. Infrared radiation is what's used in the remote controls for your PlayStation or your TV set. So to sum up, what we have here is a relationship between frequency and energy. That is, if we have shorter wavelengths, so short wavelengths means we have high frequency, and that gives us more energy, right? The high frequency gives us more energy. When we have longer wavelengths, so longer lambdas, so now these are increased, the frequency is lower, and that corresponds to less energetic. Now, while all that was going on, we had some other experiments to talk about. Now we're starting to turn to the 20th century. So at the very beginning of the 20th century, so right around the 1900s, we had some experiments done by Max Planck and Albert Einstein. Here's some pictures of Max Planck. Normally you see this more stately picture of Planck when you look him up, but I suspect this is what he looked like after celebrating from winning the Nobel Prize for the work that I'm about to tell you about here. So he was doing a lot of really interesting studies trying to understand what's called black body radiation, which we're not really going to get into a lot. You can read it in the textbook if you want. But basically, the thing with black body radiation, or just radiant energy, is that as you heat objects up, they emit light. It's called incandescence. All right, like the incandescent light bulbs, you have filaments, and you put electricity through those filaments. They heat up, and they get so hot that they start to glow. They start to emit light. That's called incandescence. Well, it turns out that when you measure that output very, very carefully, there's not a linear relationship between how much energy you put into it and the frequencies of light that come out. Right? It's not a continuous scale. Instead, Planck was able to demonstrate that the output came in little packets of energy that he called quanta. And so his theory was basically that all electromagnetic radiation occurred in these quantized energy packets. One way that I would have described this for you if we were in the lecture hall is I would climb the steps of the lecture hall and compare that to, say, climbing a continuous ramp. So if you're going, say, from level 1 to level 2 up to the top of the lecture hall, you might imagine that as you increase energy, you just glide up this steady ramp until you get to level 2. Right? That would be continuous, and that's not what we're doing here. Instead, with Planck's idea of quantization, you're at level 1, and even though you're taking on more energy, you stay at level 1 until you reach this point where now you've got enough energy to get to level 2. And all of a sudden, you appear at level 2. You disappear from level 1 and you appear at level 2 in the same instant, and you are never found in between. So it's that kind of concept that explained all of this black body radiation data that existed at the time. And we have what's called the Planck constant, H, which is 6.626 times 10 to the negative 34th joule seconds. The unit joule, that's a kilogram meters squared per second squared. This relationship that I told you earlier, the relationship between frequency and energy, but now we can relate that much more carefully using this idea of quantized energy. E is simply related to the frequency multiplied or quantized by Planck's constant. So h nu. And again, h is Planck's constant. So a very straight relationship. Qualitatively, you can understand that relationship from my description on the previous slide. And here it's shown quantized by Planck's constant. Now we also know from earlier that there is a relationship between wavelength and frequency. I showed you that one on the slide above. So wavelength times frequency is always going to be equal to the speed of light for electromagnetic radiation that's traveling in a vacuum. So we can take these two equations and rearrange things a little bit. So nu is equal to the speed of light divided by the wavelength. And then I can take this and substitute it into here, and I get a very useful equation. The energy is equal to Planck's constant multiplied by the speed of light divided by the wavelength. And the reason this equation is very, very useful is it because it relates something that we can see very, very easily. The wavelengths, you can detect that very, very easily as, say, the color of light, if you're looking in the visual range, right? So this equation will directly relate the wavelength, which we can easily detect. It relates that directly to energy, which is E, because h, that's a constant, and speed of light, that's a constant as well. So if you can measure a particular wavelength of light, you will then be able to calculate what amount of energy is associated with that electromagnetic radiation that you visualize by that particular wavelength of light. Up until this point, as I mentioned earlier, everyone was still thinking of light as traveling as waves. But that had some fundamental problems of light traveling just as a wave. It didn't explain everything. For example, if you drop that pebble in the water, over here, these waves, they propagate through a medium, right? That energy is transmitted as a wave through the medium of water. If you drop a pebble in a vacuum, you don't see any kind of disturbance wave moving through a vacuum. Same is true with sound waves. The waves radiate out. Now, those are compression waves, but they need to travel through a medium. That medium happens to be air. If you take all the air away in a vacuum, then you don't have any sound. Sound requires the medium through which those waves travel, okay? So the same is true for light. If light is really traveling as a wave, it needs a medium to travel through. But wait a minute, we can see the light from the sun, we can see the light from stars. How is that propagating through a medium to us? There's a vacuum of space. All right, so there's a problem with this. You can't just think of light as behaving as a wave if a wave requires some medium to travel through. It can't travel through a vacuum. Well, light can. So something else has to be going on with light, even though Young's experiment was quite definitive. And it's no wonder that scientists for over 100 years considered that light really behaved as a wave, even though they recognized that, yeah, there was this fundamental issue. Well, it can't be a perfect explanation because how else do we see light traveling through a vacuum? So it really wasn't until Albert Einstein came along with his photoelectric effect that started to shed a little bit of light on the situation. By the way, Planck won the Nobel Prize for this work around 1918. I wouldn't test you on this, but I just like putting all these things in perspective. Einstein won his Nobel Prize actually for this work on the photoelectric effect. All of his stuff about relativity and special relativity came later. He never won a Nobel Prize for that. His Nobel Prize came in 1921, and it was for this work on the photoelectric effect. What it's doing is showing that light can actually behave as a particle, and that was really fundamental. The setup for the photoelectric effect looks something like this. You have a vacuum tube, and you have a metal surface, and there's a gap between the metal surface and the positive electrode. And so normally you would not be able to read any kind of current going through this circuit because there's a space between the metal plate, which is the negative electrode, and the positive electrode. If you were to shine some, I don't know, let's say some red light that has a fairly longer wavelength, and we know that the longer wavelength has the lower frequency, which means that it's less energetic. Now what's not shown on here is a y-axis. That would be intensity. So you might think, okay, well the red light isn't strong enough to do anything. But what if we really turned up the gas on that red light and shined it really, really brightly? Maybe we would see something happening. Well, what would that look like on this trace? If I were to increase the intensity of the red light, I can do that and it would look like this, okay? But that doesn't change the wavelength and it doesn't change the frequency. All I'm doing is changing the intensity. And you could ramp that all the way up and you would never get this meter to show any kind of a current through this setup. On the other hand, if we took some violet light over here, now the violet light has, as we already described, it's more energetic. The violet light has a shorter wavelength, which means it has a higher frequency. And as we already described, this is more energetic. Well, even at a low intensity, what do you suppose happens if you shine ultraviolet light, or violet light for that matter, or even blue light, onto this metal surface? Well, if it's blue light or violet light shining on, all of a sudden you get this meter showing that there's a current, even at lower intensities. All right, whereas you would shine red light and you can crank it up all the way to 11 and you would never get that meter to move. And Einstein's explanation of this was that the electromagnetic radiation actually had a particle component to it, such that when the frequency was high enough, such as the case with the blue or the violet light, that the particles provided enough energy to physically kick electrons off of the surface of the metal to complete the circuit. And this was independent of the intensity of that electromagnetic radiation that was found at the lower frequencies. And they were actually called photoelectrons. And particles don't need a medium in order to travel through it. Particles can travel through the vacuum of space, just like comets, planets, right? Those are particles that can move through the vacuum of space. Now, that didn't mean that everything else for hundreds of years leading up to this experiment, it didn't mean that that was wrong. But Einstein's revelation was that light can really behave as both a particle and a wave. It's what we call the duality of light, right? It can behave like a particle and it can behave like a wave. It really depends on what experiment you're doing. All of these ideas come together as now we in lecture talk about other experiments that take this a little bit further and then start to draw upon some of these more fundamental experiments that were done to overall pave the way into the modern quantum mechanical atom, which is our best explanation to understand all of the scientific data that we can collect to understand atomic behavior. So we'll pick it up in lecture, and I'll see you then.